Hi there. It is Physical Science Coach Mr. Powers. And here we are today talking about gravity. It's going to be a good time. I think you guys are going to enjoy this. This is section 12.2, and we are going to be talking about gravity and projectile motion today, talking a little bit about space. It's always fun to kind of get into the space of things. So let's go ahead and get started with these objectives. You are going to be able to explain the effect of mass and distance on gravitational forces. We're going to talk about what gravity really is. We're going to explain the effect of mass and the free fall acceleration of an object near the Earth's surface. And we're going to distinguish between mass and weight. And we'll also talk about some projectile motion. All right, so our weight and our mass are different. We're going to create a little table here in just a second that'll kind of highlight some of those differences. But we want to remember that weight has to do with the effect of the gravitational force. Mass has nothing to do with gravitational force, but weight does. So when we think about weight, we need to start thinking in terms of gravitational force. And again, it's going to be different than mass. All right. So we've got to have the gravity as part of our definition when we talk about weight. Weight is measured in newtons, okay? And when we talk about mass, we're talking about kilograms typically, right? You might be talking about pounds, but pounds is actually a weight, and mass is actually not considered, well, pounds is not considered a mass, let's put it that way. All right, so our formula for weight, we'll talk about this here in a little bit more too, is mass times acceleration due to gravity, okay, or times what we call the free fall acceleration. And remember that mass is the amount of matter in an object. Remember, that's different than volume. We oftentimes have students just kind of confuse the difference between volume and mass. Volume is the amount of space that something might take up, but mass is the actual amount of matter, that substance, and it has nothing to do with the amount of space it takes up. All right, so let's look at some of these things that we should hopefully now know. Let's see if we can review this a little bit. So weight, again, downward force of an object due to gravity. Our weight is going to be measured in newtons. Okay, that's the one we want to talk about. You know, we might, know from the system that we commonly use, we might know pounds, but really, let's not focus on that, right? Newtons, ooh, this is a new one that we get to learn. Remember what newtons are. Okay, a newton is a measure of the force of something, and so this is the force of your body against the earth. Basically, it's how many newtons you have. Remember, mass is measured in kilograms or grams, and free fall acceleration, this is acceleration, so remember, acceleration is meter per second or meters per second squared. Remember that the g value here is going to vary by location. Different planets are going to have different g values because they're going to have different gravity, right? So your free fall acceleration due to gravity, that's probably where that g came from, right? That is going to be different on different planets, okay? And if you have different amounts of gravitational pull, you're going to have different g's. And we'll talk more about the formula for gravity in a little bit here. All right, so mass and weight. Mass is the amount of matter, but weight is the downward force of gravity that's being pushed, right? So again, we can kind of think of gravity being involved here when we're talking about weight, where it's not involved with mass. The mass is not dependent upon location, so I could be floating in free space and I would have the same mass as if I were on Jupiter, right? Mass is not going to change, but weight is going to change. Weight will be much greater on Jupiter than it is on the moon, for instance, our own moon. So if we were to do some calculations and we were to try to say, hey, what's Mr. Wonderful's mass on Earth? If it's 80 kilograms on Earth, what would it be on the moon? It's still 80 kilograms, okay? So the mass doesn't change on location. But if Mr. Wonderful's weight on Earth, let's say were 600 newtons, all right, that's not the same as 80 kilograms, by the way. If it were 600 newtons on Earth, then what would it be on the moon? It would be 100 newtons, okay? Basically, the moon is about 1/6 the gravity of the Earth, and so it's going to have about 1/6 the weight on the moon that you would have here on Earth. What really is 80 kilograms in terms of newtons. Well, we'll learn about that a little later. All right, so why do objects fall to the ground when dropped? We have to ask ourselves these questions. At one point, people didn't really ask that question, but then somebody asked it. You guys may have heard of, Newton being asleep under the tree. And then a little apple. We should do an apple. It's going to be red. Yeah, that's going to be cool. Little apple tree. Bloop, 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 bloop. It's a yellow apple tree. And one of the apples, they say, falls and hits him on the head, right? And then, oh, yes, let me think about gravity. That story is probably anecdotal, probably not true at all. But we do kind of think about that story and hear about that story. Whether or not it's true or not, might be an entirely different matter. But at any rate, why do objects fall to the ground when dropped? We know that Newton was asking this question at some point or another, whether or not he was hypothesizing somebody having their, head beat with an apple or not. That is one subject or another. But we have to figure out that there's something that pulls these objects to each other. And remember that Newton had a very different idea than Einstein. Okay, so Newton was way earlier than Einstein, but Newton came up with an idea. And he came up with some laws, and then Einstein came around later, and he had a totally different way of describing it. We're not really going to focus on what Einstein talked about. We're going to focus on what Newton talked about, even though Einstein, is really more of the common current thinking. The physics behind Einstein's thoughts are a little bit more complex. So we're just going to focus on classic Newtonian physics, as we call it. And so we'll talk about the universe in terms of the way Newton saw him at this point. So all objects in the universe are attracted to each other through the force of gravity. Objects that have mass are going to be attracted to each other. Okay, so basically, if you have any two masses in the universe, those objects are going to be attracted to each other. Now, the degree of attraction is going to have a lot to do with two big factors. Okay, one of them is the size of the mass. I keep changing ink colors here. You'll notice this one is 2 meters. This one's 1 meter, okay? Now, the distance here is the same, right? Distance is the same between these two balls, but this one is going to have a bigger, okay? It's going to have a greater gravitational force. Why? Because it has a bigger mass, right? So if you have bigger mass, you're going to have greater gravitational pull, right? So the mass here is just 1m, and here you have 2m, all right? That's 2 times the mass, basically, is what they're trying to show here. The other thing that will really affect the gravitational pull is the distance. Look at how big of a distance we have now. So compared to this distance here, it's quite a bit different, right? And so if you have greater distance, then you're going to change your gravitational pull. And the further you go away, the less of a gravitational pull or gravitational attraction you're going to have. Now, which one matters more? Distance or mass when it comes to the pull? Well, let's look at the equation and let's see if we can figure it out. Now, first of all, when we start this equation, you're going to see a G here, and we're not really going to talk about that G. That's called the universal gravitational constant, okay? And we don't have to worry about that until we get into physics, but just let it be known that that's a very big number, okay? But look here, that we have the masses that are at play. And so those two masses, whatever they are, they're going to be multiplied by each other. So the mass is going to definitely affect the total force of gravity. But look at the distance. It says that we're dividing our overall masses multiplied by each other and multiplied by the universal gravitational constant, and we're going to divide it by the distance squared. So that means that every time you increase your distance by a factor of 1, then you're squaring the effect that it's going to have on the object. Okay, so let's see if we can fill out some of these, see if we can figure it out. If I increase my mass by 3 times, what's going to happen to the force? Well, basically just imagine that you've increased that number, whatever it was, by a factor of 3, right? And so if this was a 1, and I increased it by a factor of 3, it's now a 3, which means that the F value over here now is going to be 3 times bigger. So if I increase my mass 3 times, the force is going to be 3 times bigger. However, look at this. If my distance is increased 3 times, Now I'm dividing, let's say instead of dividing by a 3, I'm increasing that by 3 times. And so that would be like 3 squared, right? Okay, so if I were originally dividing by 3, which is actually dividing by 3 squared, which is 9, now let's assume that I'm increasing my distance 3 times. So instead of 3, I'm now at 9. And so that means my formula is 9 squared, which means I'm actually dividing by 81 now. Although I only increased by a factor of 3 here, I increased by more than that, all right? 3 times 3 is 9, but 9 times 3 is 27, right? So I have increased this quite a bit more. I've increased it, to 9 times 9 instead of just 9 times 3, right? And so I'm increasing it by a squared factor. So if distance is increased 3 times, the force will decrease, okay? By the way, this one was increased 3 times. The force will decrease because it's being divided by 9 times. Okay, so it's a squared factor. So distance actually has a bigger effect on gravity than the mass does. And this is why we can go up into space and, we can be not that far into space and we are not going to have as much of an effect of gravity. Now, when you think of free floating in space, I want you to start getting out of your mind right now that you're not being pulled by gravity. We'll talk about that here in a second. But being in free fall up in space where you just feel like, oh, I'm floating, you're actually still falling. And gravity is still pulling on you plenty strong. It's pulling you right back to Earth. But you're also going so fast that you just kind of spin away and get away from actually hitting the ground at the time. You're like, what? Yeah, it's true. All right, so we'll talk about that here in a second. So the gravitational force increases as mass increases or distance decreases, right? So if I want to increase my gravitational force, I've got to decrease my distance. Did you know that if you go up on top of a mountain, let's say this is our little mountain, I've got a little guy up here, whee! Did you know that because you are further from the center of gravity on the planet, that you actually have a lower weight? That's actually going to decrease your weight, okay, the higher you go. So that means that you actually weigh more down here in town than you do when you go up in the mountains. Now, is it something that's measurable? Yeah, it would be measurable. Is it something that's measurable by you or me with our equipment, like scales? No, our kind of scales aren't going to measure that. But the weight does change because you're further from the center of gravity. Your distance up here has increased, and so you're actually changing your weight. Pretty interesting, right? All right. So let's talk about free fall acceleration. Free fall acceleration basically is another way of describing the acceleration due to gravity. All right. Here on Earth, we typically describe this as 9.80 meters per second squared. 32 feet per second squared is kind of what we would talk about if we were talking about it in terms of feet. But this means that I'm going to accelerate faster and faster as I fall. Okay. Now, that's assuming that there's no air resistance. Now, if there is air resistance, then you're going to see that I'm going to hit terminal velocity. Okay, it's the maximum velocity that's reached by a falling object. And why does it reach a maximum velocity? Because the force of the air resistance eventually is going to equal and balance out to the force of gravity. And so it's going to give you a constant velocity, okay? Now, when I'm using a parachute, I'm increasing my overall surface area, so I'm increasing my air resistance, and so that's going to slow me down even more, which is what we want. But did you know if we were to go on to Mars and we were trying to like parachute on Mars, we would be in serious trouble. The atmosphere is not thick enough on Mars to actually hold us up at a speed or slow us down, basically, enough to keep us from injuring ourselves as we land. And so when they come up with the ways to land on Mars, they have to think about new and innovative ways to land that aren't just parachutes, because the parachutes aren't good enough to prevent damage from the structures because you just don't have enough air resistance. And so your terminal velocity is a lot higher on Mars than it would be here on Earth if everything else were, about the same. So anyway, kind of interesting there. All right, so in absence of air resistance, all objects falling near Earth's surface are going to accelerate at the same rate, regardless of their mass. And again, this is free fall, the motion of a body when only the force of gravity is acting on the body. So if we have no air resistance, then we can measure very clearly, okay, the actual effect of free fall. So for instance, if I start at 0 and after 1 second, because I'm traveling at 9.8 meters per second downward, I am going to be reaching 4.9 meter distance by the time I've traveled 1 second. Okay, well, what happens in the second second? Well, in the second second, again, I'm still accelerating 9.8 meters per second, which means every second I'm getting 9.8 meters per second faster. So now I'm getting even faster than the 9.8 meters per second. And so now I'm at 19.6 meters per second traveling down, which means I will have now traveled 14.7 meters, okay? And in the third second, I'm going to be traveling even faster at 29.4 meters per second. So that means I will have traveled 24.5 meters by that time. And so you're just going to get faster and faster and faster as long as there's no air resistance. Of course, here on the Earth there is, and so you're going to hit terminal velocity. But astronauts, once they get up past the top of the atmosphere, where the atmosphere is really has any sort of significance in terms of particle number, then you really don't have any air resistance, right? But you still have gravity. And astronauts that are in orbit are in free fall. They're continually falling. I'm going to show you a little graphic here that's going to kind of explain that here in just a second, okay? So just think though of an astronaut or a spaceship orbiting around, a satellite orbiting around the Earth is actually continually falling down, all right? Orbiting around is one way to think about it, but it's actually more accurate to think about it as falling down. All right, so projectile motion. You're like, what? Trust me, I know it hurts my head too. Why does a projectile follow a curved path? Now, we've got to talk about projectile motion right now because we have to help you understand why it is that these objects in free fall are just falling, right? Even though they're moving. All right, so projectile motion has two components, horizontal and vertical. When the two motions are combined, they form a curved path. Okay, so projectile motion then is defined as the curved path that an object follows when thrown, launched, or otherwise projected near the surface of the Earth. Okay, so you can imagine if I had, the surface of the Earth and I wanted to launch a missile somewhere and land somewhere else on the Earth, that missile is going to have an upward motion. It's going to have a sideways motion, right? It's going to have a projectile motion, which is horizontal in component and vertical in component. Now, the horizontal part is the part where it's moving along the Earth, right? The vertical part is the part where it's going up away from the Earth, all right? So think about a ball. If you just think about a ball, not necessarily a missile, if you throw the ball, once you've thrown that ball, the ball does not have any way to accelerate itself and keep going faster, right? If I'm playing volleyball, once I hit my serve, I've hit it as hard as I'm going to hit it. It's not going to get faster. It's only going to slow down based upon wind resistance, right? So no horizontal forces are acting on the ball if you ignore air resistance. Air resistance could still do that, right? Think about a bullet being shot from a gun. Not much air resistance there, right? It's a pointy little bullet. It does have some, though. So the horizontal component of velocity of the ball is constant after the ball leaves your hand. So once that ball leaves your hand, here you are throwing the ball. Whee! Okay, once you throw that ball, that horizontal component, this component here that moves in this direction is constant. It is not changing, all right? You gave it a certain amount of energy, and it keeps that energy unless air is striking against it, which, again, of course it does. But, again, we're assuming that resistance is being ignored. Air resistance is ignored. So projectile motion has a vertical component as well. So we got to think about this part now we know is constant. But what about this part that goes up and down? When you throw the ball, the gravity is going to immediately start pulling it downward. So imagine myself, okay, and I throw the ball up. Whee! And as soon as that ball leaves my hand, it is going to start slowing down. And it's going to slow down until it gets to the top of its throw. And at the top of its throw, it's going to be traveling at 0 meters per second, right? Again, we're assuming no air resistance here. But gravity is going to pull on that thing until it gets to the top of its trajectory, and then it's going to be pulling it down. And it'll pull it down at the rate of 9.8 meters per second squared, just as it pulls down every other object, right? And so I can measure very clearly what that looks like. So let's look at it. if I take, let me change my color pen again here. If I take my sphere and I drop it out of my hand here, and at exactly the same time I shoot it out of a cannon over here, okay, these are cannonballs, and I measure the time intervals, okay, at time interval 1, whatever that interval is, they are exactly equal to each other, okay, that's the idea here. At time interval 2, they're exactly equal to each other. Time interval 3, they're exactly equal to each other. Now this one is still moving in this direction because it had a horizontal component, but the vertical component of these two is going to be the vertical component of these two is going to be exactly the same, and they're going to fall and hit the ground at exactly the same time. Okay, now, that kind of seems weird, but you could shoot a bullet out of a gun, and if it was exactly straight, and then you drop the bullet at the exact same time, that bullet that shot out of the gun might land a mile away, but it will land at exactly the same time as the bullet that was dropped from your hand. Now, if you could do an experiment that accurate, it's really hard to do an experiment that accurate, but you can do experiments with little balls that are falling off of tables and stuff. And we do this at school, and I have a device for it. So when we get to school, if you want to see it, let me know. Okay, so that gives you an idea about projectile motion. Now let's look at this little planet here and the space shuttle moving around the planet. Okay, so what you have to think about here is that this space shuttle is being pulled toward Earth, right? We've got that little arrow pulling the space shuttle toward Earth. It is being accelerated toward Earth by the force of gravity, okay? And we do, however, have a motion that is in this direction as well. It's a horizontal component, right? And so because this thing is moving forward, then what happens is that, whoa, what happened there? What happens is that we have a combined motion that is a projectile motion that keeps this thing moving around the Earth all the time. Kind of imagine that you are walking on some sort of escalator, right? So let's say you've got an escalator and you're walking on that escalator, and imagine that you are walking backwards, right? So the escalator is going in this direction, and you are walking in this direction, right? You guys have done this before. And if you walk at exactly the right pace, then you stay in place, right? You keep stepping down. You step down over and over and over again, but you're not going anywhere, right? So imagine that. Like, I step down, but because the escalator is moving back in this direction and that down just keeps disappearing, then I stay in motion. I stay in place, sorry, and I'm not really in motion. And that's what's happening here with the space shuttle. The space shuttle continues to fall, but because the Earth is just disappearing out from underneath it, right? Imagine the Earth now, and it's spinning around. The Earth is spinning, and I'm falling down, but because the Earth continues to spin and I'm also moving in this direction, right, that I just keep going and I keep falling forever. All right. Now, you don't always fall forever because eventually satellites are going to degrade in their orbit. They're going to crash down to Earth and things like that. But it's just really cool to think about the fact that we are actually continually, if we're up in space, we're continually falling down, but we just never hit the ground because we're moving forward at the same time. And so the ground keeps disappearing out from underneath us, kind of like this escalator, right? So it's kind of the same thing. It's kind of wild to think about, but that's what's happening, right? And again, it doesn't matter which direction the Earth is spinning, right? The Earth could be spinning in one direction or the other direction, and it wouldn't matter because this projectile motion here is continuing to go forward. That's what keeps you from ever hitting the ground. If you just shot a rocket straight up, is it going to just spin and go into orbit? No, you've got to. And if you watch these things blast off, they always kind of blast off at an angle, right? And they're going to stay working at an angle. They got to get some horizontal motion going, because if they were just to go straight up, they would come straight down, even if they left the atmosphere. Okay, the atmosphere does not suddenly make them float, right? Being past the atmosphere, gravitational force is strong enough way out there to still pull you. And in fact, think about the moon. The moon is in a free fall around us, and we are in a free fall around the sun. Like, we are being pulled toward the sun because the gravitational forces are so strong, and yet we don't ever hit the sun because we're zipping around it, and so we're continually falling toward the sun but never hitting it. Okay, now it's wild to think about that. These huge planet is falling toward the sun, right? It's amazing how strong this gravitational force is, and yet it's the weakest of the forces. Isn't that wild to think about? The gravitational force is the weakest of the forces. All these other forces are even weaker. Anyway, we've learned a lot. We've learned even more than what's up here, but let's talk about what we've reviewed. Review what we've learned about. How are mass and weight related? Well, we now know that they're both dependent upon the amount of matter, right? But weight is dependent upon the location and mass isn't. And we know, of course, that weight is measured in different units and mass, things like that. Why do objects fall to the ground when dropped? Because of this force of gravity. Now, you might be at this point thinking, what in the world is gravity? What makes gravity work? What is behind it? We don't know. And it's okay, right? These universal forces, we've got these 4 universal forces. We can't really explain them. We can't explain why they work according to Newtonian physics, all right? But we just know that they do. We see them. These are mathematical laws, right? We see what happens. It's the what. We talked about the difference between theories and laws, right? Well, this is a law. It's a what. It's the law of gravity says, hey, you're going to have attraction between objects. Why? Yeah. Right? We don't necessarily have to answer the why, right? That's not necessarily what we answer in science all the time. We can tell you the what, and we can describe a mathematical formula. We can show you it's true over and over again, drop pens over and over again. It's true, but we don't necessarily tell you why. And that's okay in science. We have to be okay with that. All right. What is the relationship between free fall acceleration and mass? Well, the bigger the mass, is that going to change your free fall acceleration? If I have a 1 kilogram mass and 1,000 kilogram mass, are they going to fall at different rates? No, they're going to fall at the same rate. So the acceleration is going to be the same as you're pulling. Now, you might be thinking, I don't know. Powers, I think I watched a video just the other day, and it was talking about inertia and that they might actually be different. Okay, so there's another way to explain it, right? You can explain that the larger the masses, the larger gravitational force there is. Well, that's true, right? We can see that from the formula right away. But then you're like, well, so then if there's a larger gravitational attraction, why are they not traveling at different speeds? Well, the explanation for that is that one of them is going to have more inertia that has to overcome. So the bigger masses are going to have more inertia that they have to overcome. And so they will fall at the same speed as a smaller mass because it has less inertia to overcome. That's one way to explain it. But what you really have to know is that despite the mass, these objects are falling at the same rate. And so while their gravitational pull might be different, they might have different weights, the free fall acceleration stays the same. 9.8 meters per second squared is going to be the same for that object that is falling that is really big and that object that is falling that is really small, okay? And they'll hit the same terminal velocity if they have the same density and the basically the same surface air resistance. They're going to basically have the same terminal velocity as they fall. One really big, one really small, they'll still fall at the same rate, even with an atmosphere, okay? Anyway, lots of cool stuff. I hope you enjoyed it. Gravity is fun to talk about, and I hope it was fun to learn. You guys have an awesome day. Be kind to one another. God bless you, and we'll catch you on the other side of